Hey everyone, this is Daniel for Rock the JVM, and you are watching a comprehensive tutorial to Java virtual threads. So virtual threads are one of the most exciting features to come in the Java world in recent years, and this tutorial is a very code-focused guide to Java virtual threads. And here we're going to discuss differences from the normal ways that we can spawn and delegate tasks to threads, with lots of examples and code. We're also going to discuss some internal implementation details that make virtual threads special. Now, as always, with the rest of the Rock the JVM tutorials here, I recommend that you write code with me to make the most out of this video, and whenever you need to refresh your memory, just refer back to this video or to the written form at the blog with the link in the description. The blog post is a very comprehensive guide in written form on virtual threads, and you will also find some external explanations about virtual threads and how they work that we might not necessarily have time to discuss in this video. The blog post will also contain code snippets that you will need to set up your own project, for example, to set up your own module, as well as the POM XML, which you can find at the end of the page with all the plugins and the dependencies with libraries. And we're only going to use Lombok and Logback Classic just to add some logs and to write code a little bit more quickly. So bookmark the blog post because you're going to need at least some snippets, and I'm going to describe what they are. Now, here I am in my development environment. I've already set up some code so that we can get started much more quickly. This is a plain IntelliJ project with just a simple class that I called virtual threads with a main function that we can run as a standalone application. The POM XML contains everything that the blog post also shows you. I'm using JDK 20 at the moment of this recording, but you can also use JDK 19, which is the first official preview release of virtual threads. So you can use JDK 19, 20, or if you're watching this video a little bit later, even later JDKs. I'm only going to use Lombok and Logback Classic as library dependencies. And as for the module info, here under my source main Java, I have a package called Rock the JVM, and I have a module info where I'm requiring the concurrent package, which is including the virtual thread specification, which is not really part of the official JDK API, but it's part of the preview API, so this is why we are adding it here. I'm also requiring SLF4J so that we can have logs, and also Lombok with a little annotation so that we can write code a little bit more quickly. So if you want, you can pause the video and set up your own project with a POM XML and module info. Now, my virtual threads application will have a simple logger that I'm going to use to write things to the console. I have a function here that I call the log that includes the message and the thread that executes or evaluates that message. And I also have a utility function that I called sleep for a particular duration, which only uses thread.sleep. But because we're going to use this quite a lot, and because thread.sleep throws an interruption exception, or whatever the exception is called, which is a checked exception, I'm using this sneaky throws annotation from Lombok so that we can write code a little bit more quickly. And this turns the checked exception into an unchecked one so that we don't have to wrap our code into nested try catches. So don't use this in production, just for this demonstration so that we can see how virtual threads work. So if you want to pause the video to set up this kind of code, feel free to do that now. I'm going to get started on what virtual threads are. Now, so far at Rock the JVM, we've discussed in various tutorials a variety of ways to run concurrent code on top of a small number of operating system or JVM threads. And that includes Akka with the actor model. We have Scala with fibers in Cat's Effect and Zio. We have Kotlin coroutines. And there are all ways to run concurrent code on a small number of threads. So with Akka, we spawn millions of actors that we can send messages to. With fibers, we have so-called green threads that are simple data structures that are scheduled on a collaborative thread pool. Coroutines are a similar way to do that in Kotlin. Now, recently, JDK introduced virtual threads. Now, as we already know, the JVM gives us an abstraction over operating system threads with Java-lang threads, so we're using the thread abstraction here. Now, until Project Loom, which is essentially what we're discussing in this video, every thread in the JVM is just a wrapper over an operating system thread, and we call those operating system thread, OS or JVM thread, as a platform thread. Now, the JVM thread was just a data structure that wrapped an operating system thread, and whenever you wanted to run any code on a JVM thread, this will spawn an actual operating system thread which executes that particular bytecode. Now, the problem with platform threads is that they're very expensive from many points of view. So they occupy a lot of memory and they take a lot of time to either create and or destroy. So I'm going to give you an example of how and why these operating system threads are quite expensive. So I'm just going to write a static function. I'm going to call this, let's call this example. And this example will have a for loop, let's say I from 0. I'm going to spawn, let's say, 100,000 threads. So I'm going to use 100,000, and I'm going to run something like new thread, where I'm going to run a simple lambda, let's say try, and I'm going to say thread sleep for duration dot of seconds 1L, and I'm going to catch with an interrupted exception. And with this catch, I'm going to say throw new runtime exception with that E. So I'm just wrapping this over a unchecked exception. And I'm going to say start. So I'm essentially going to start 100,000 threads. Now, with the regular thread constructor, this actually spawns an operating system thread. So this example, let's just remove this system out print line. This example, I'm going to also print line. So sys out, I'm going to say threads done or something like that. And I'm going to run this application. And after a certain time, we'll see that the JVM will crash because the operating system cannot spawn that many threads. Now, we have to enable preview to run this application. So let me go collapse that, and I'm going to go to my project structure. So file project structure, and I have my SDK here under the actual first item in this menu. So under project, we have JDK 20, and at language label, I'm going to select 19 preview. I'm going to also click apply and then OK. And I'm going to edit the run configuration here. And my run configuration needs to take a little VM arguments. So program arguments here, I'm going to use -- enable -preview. So that's going to be my command line option there. So let me go run my little application, and it's probably going to take a little time before it crashes, but 100,000 threads is going to definitely crash. So I'm going to speed time up a bit. And we're 10 minutes later, and apparently the threads are done, and I did try with 1,000,000 threads. Apparently the computer that I'm recording this is quite powerful, but they didn't really sleep for just 1 second. So in theory, if you wanted to spawn 1,000,000 threads and each would sleep for 1 second, they should in theory be done at the same time. The problem is that I'm spawning 1,000,000 threads and they are done after 10 minutes instead of 1 second each. So this goes to show how expensive these threads are. Now, depending on the kind of computer that you're writing a code on, if you're following this video as I'm doing this on camera, you may actually find that your JVM will crash outright. So this is just a testimony of the fact that an operating system thread is very expensive to start and also stop, which is why we have this construction of a virtual thread. A virtual thread is just a data structure that the JVM will then use to schedule these lightweight applications, these lightweight threads on top of a few operating system threads. So a virtual thread is a new type of thread that tries to overcome the resource limitation problem of platform threads. They are an alternate implementation of the same type, which is Java-lang thread, but the data that that thread needs to run on, which is, for example, the stack of that particular thread, is actually stored on the heap, not on the JVM stack. And this makes sure that the virtual thread is treated like just a plain data structure that is being passed around between a small number of platform threads. And I'm going to show you how we can do that. So I'm going to say a private static thread, let's call this virtual thread, and I'm going to have a string name and a runnable that I'm going to run here. So I'm going to say runnable, and I'm going to return thread dot, and we have a construct called of virtual, and then we have dot name. So this is kind of like a builder pattern. Start with runnable. So notice that we have this little extra API here, thread.ofVirtual, but the object that we are going to return here is, again, an instance of the same type Java-lang thread. So from the user's point of view, the thread API is intact. Now, let me simulate virtual threads with a little example that I also used in the Scala tutorials for fibers and also for the Kotlin coroutines if you want to compare virtual threads with those approaches as well. So I'm going to simulate a morning routine where I'm going to heat up some water for some coffee. So boil some water for coffee or tea while I am taking a shower. Now, assuming this is all safe and well in the real world and no fires are starting in the house, I'm going to have a static thread. Let's call this bath time. And I'm going to say return virtual thread. So I'm going to call this little method that I created prior. I'm going to call this bath time. And the runnable that I'm going to run is a simple lambda that I'm going to use log with I'm going for a bath. And I'm going to sleep for duration of millis. And I'm going to have, let's say, 500 millis. So I'm going to sleep for half a second. And again, I'm going to log I'm done with the bath. Okay, so I'm going to simply run a virtual thread that does all these things. Now, another thing that we can run is to boil some water while I am taking a shower. So I'm going to say static thread boiling water, and I'm going to return a very similar thing. So I'm going to copy most of this code so that I don't type it by hand. I'm going to say return virtual thread. I'm going to say boil some water, boil water. And the runnable that I'm going to say is I'm going to boil some water for some tea. So I'm going to boil water for some coffee or tea. Now, with that statement, I'm probably going to offend some people because I know there are some coffee lovers among the audience of Rock the JVM. And I'm going to sleep duration of millis, let's say, for 1 second. So 1,000 millis. And I'm done with the water. Okay. Now, boiling water and bath time. Let me run both at the same time. So I'm going to say static void. I'm going to call this concurrent morning routine. And I'm going to start both. So I'm going to say var bath time as bath time. And I'm going to use type inference here with the var keyword. I'm going to have a var boiling water as boiling water. Now, when I say bath time and boiling water, they start the virtual thread. So the virtual thread method actually does start the thread. So all I have to do is join them now. So I'm going to say bath time join, and I'm also going to have boiling water join. So let me go run this whole thing. So bath time join, boiling water join. These things throw the interrupted exception. So I'm going to annotate this with add sneaky throws so that I hide these. And I'm going to call, let's say, concurrent morning routine, just so that we see that both of these virtual threads run at the same time as expected. All right, so we have the following logs. I'm going for a bath. I'm going to boil water for some tea. So notice that both of these virtual threads start at the same time. I'm done with the bath. I'm done with the water. So I'm done with the bath, and by the time the kettle has finished boiling the water, I'm there to receive it. So both of these virtual threads run at the same time. Now, the main advantage of virtual threads is that you can spawn millions, tens of millions of virtual threads on relatively few JVM threads like 6 or 7 or 10 or something like that, and the JVM will not even break a sweat. And the thread API is intact, as well as ExecutorServices. So let me show you an alternative way of performing this morning routine with ExecutorServices. So I'm going to have a small example with executors on virtual threads. So let me have a static void, let's say concurrent morning routine with executors. And you know from the regular Java threads that you can run an executor service. So I'm going to run a try with resources. So try, and I'm going to have a var executor as executors. And going to import that executors new. And you can have single thread executors and so on and so forth. But the thing that I wanted to use here is a virtual thread per task executor. So new virtual thread per task executor. So whenever you submit a task to this executor, it will submit a new virtual thread. And I'm going to have a bath time and a boiling water to run my little runnables. So I'm going to have my var bath time as executor.submit, and I'm going to submit this runnable. So I'm going to go for a bath and so on and so forth. So I'm going to use that. Then I'm going to run my boiling water. So I'm going to copy the runnable there. So I'm going to say var boiling water as executor.submit, and I'm going to use the exact same lambda there. And I'm going to say bath time get, and I'm going to say boiling water get. So boiling water dot get, and I'm going to rename this to boiling water, assuming I can spell properly. And the get methods, because they throw interrupted exceptions, I'm going to also add sneaky throws to that. So this is an equivalent way of running the same thing. And whenever you do executor.submit, this runnable starts a new virtual thread. And this is going to be a future that you can block to get a value on, which is equivalent to joining the virtual threads. And I'm going to say concurrent morning routine with the executors, and this will run in the exact same style. So we have, I'm going to go for to boil some water for some tea, going for the bath, and then done with the bath and done with the water because the bath takes a little shorter. So notice that we have the virtual thread #21 runnable at, and we have a fork join pool here that we are going to use for scheduling these virtual threads. Now, if you want to name these virtual threads so that we can debug things more easily, you can have a final, let's say, thread factory as thread of virtual, and then name. And I'm going to call this routine dash, and I'm going to start at 0, and I'm going to say factory. And this factory we can pass to this executor. So I'm going to say new thread per task executor factory. Now, the constructor here is new thread per task executor, and the thread factory is a virtual thread constructor. So we still have a virtual thread constructor per task. So whenever we do executor.submit, this will still create a virtual thread because this factory does that. So we can run the same application, and we're going to see some more descriptive thread names when we submit these tasks. Okay, so we have virtual thread #21, and notice that we have routine 0, routine 1, routine 0, routine 1, so that we know which log occurred from which thread if you want to debug a concurrent application. Now, the way that virtual threads work is that we have a fork join pool, which is a collaborative thread pool, which automatically deschedule a virtual thread once we get into a blocking situation. So normally with a platform thread, we when we do sleep, we'll actually block the OS thread, if not in the virtual environment. So if we hadn't built a virtual thread, this sleep would actually have blocked the operating system thread. But because we're doing virtual threads, this sleep is just a semantic blocking, because at this point, the blocking will not happen, but rather the virtual thread is descheduled from the platform thread. And the platform thread is now free to take on some other thread so that our concurrent application can scale. So the virtual thread is descheduled from the OS thread, which is called the carrier thread. And the carrier thread now is free to pick up some other virtual thread so that we can run multiple things at the same time. Now, of course, the JVM has a smart mechanism to reschedule this thread once the sleep is done, and we can then go on with our work once this virtual thread can execute on another carrier thread. Let me show you an example of how that would work. So let me first create a static method, static int. I'm going to say number of cores so that we can spawn at least that particular number plus a certain amount so that we can have a limited number of platform threads and many virtual threads. So I'm going to say return runtime, get runtime, and I'm going to say available processors. And I'm going to create a small function, let's say void, let's say view carrier thread pool size. and I'm going to have a thread factory. So I'm going to say final thread factory. I'm actually going to copy this one from the previous function. So thread factory, I'm going to say try on a var executor as executors new thread per task executor on this factory. So we know for a fact that we're going to spawn virtual threads. I'm going to run something like instream range. I'm going to say 0 number of cores minus 1. So I'm iterating between 0 and the number of cores. Dot for each. Now instream needs to be imported, so I'm going to say for each. And for every I, I'm going to say executor.submit. And I'm going to run a small runnable saying log with hi from virtual thread. And then I'm going to say plus I. And sleep for duration of seconds 1L. So I'm going to sleep for 1 second. Now, when you say in-stream range 0, and I'm going to use a number of cores here, the number of virtual threads spawned is equal to the number of cores. But if I try to spawn more, so I can say number of cores plus 1, for instance, if I have, let's say, 6 cores on my machine, I'm going to spawn 7 virtual threads. So let me try running this function to see how it works. So I'm going to say view carrier thread pool size, and I'm going to run this little application. And we're going to inspect the logs to validate the little theory. So I have a MacBook Pro with 6 cores with 2 threads each. So I have 12 virtual cores. So I should be able to spin up 13 threads. So I have threads from 0 all the way to thread number 12. So I have thread 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we have 13 threads in total on top of 12 normal cores. So that means that at least one carrier thread, which is fork join pool with this identifier, needs to occur twice. And it just so happens that fork join pool -1 worker 2 handles virtual thread 1 and virtual thread 12. Now, there is no determinism here, but a worker thread, which is a platform thread, needs to necessarily run 2 virtual threads at least, which is our case as well. So we can see how we can run more virtual threads than we have platform threads for. And this is very, very powerful. As I mentioned, you can spawn millions of threads on just a few dozen platform threads, and this will scale your application quite well. Now, the next thing that I wanted to show you is a sneak peek into the implementation of virtual threads. So virtual thread, I'm actually going to type this so that I can navigate to it. Virtual thread extends base virtual thread. There is a method called create default scheduler. This is a fork join pool that will have the scheduler necessary to allocate virtual threads on a small number of platform threads. And as we can see, we have a standard fork join pool, which can be configured by parallelism, max pool size, and min runnable. These are the configurations that you can use on the application that you want to run virtual threads on. And parallelism is the parallelism level, which by default is the number of available processors. Max pool size is the maximum number of platform threads allowed, which is by default 256 if you don't configure that. And min runnable is usually half the pool size. So notice that we have min runnable, integer max, parallelism divided by 2, and 1. So at least 1, and the pool size divided by 2. And this just instantiates a fork join pool, and the tasks allocated to virtual threads are simply enqueued to be run on this fork join pool. And the virtual thread is the one to be unmounted or to yield the carrier thread so that it can do something else. And I would like to show you an example of how to do that. And where are we? On virtual threads, our little application. So here under virtual threads, I'm going to run a static thread. I'm going to say work hard. And work hard returns virtual thread with the name, let's say, working hard. And the runnable that I want to run here is something that doesn't sleep, but something that's very CPU intensive. So I'm going to say log I'm working hard. And I'm going to say while, and I'm not going to use while true here because this will be optimized by the compiler. I'm going to run a small function, static, Boolean, always true. and this returns true. So I'm going to say while always true, I'm going to do nothing. So this is very CPU intensive. And I'm going to say while always true, whatever. And after that, I'm going to run a small sleep for duration of millis, and let's say 100L, so 100 millis. And then I'm going to say I'm done with the work. So I'm going to run a thread that actually consumes CPU cycles. Now, I'm going to also create another thread. So I'm going to say static thread, take a break. And I'm going to return virtual thread with the name taking a break. And I'm going to run the following runnable. I'm going to say log I'm going to take a break. And then I'm going to simply sleep. So sleep for duration of seconds 1. And then I'm going to say log done with the break so that I know when I'm done. And this is what I'm going to do here. I'm going to run both of these threads, working hard and take a break at the same time. So I'm going to say static void work hard routine. And I'm going to say var working hard as work hard. And I'm going to say another var taking break. And I'm going to say take a break. And I'm going to join both of these. So I'm going to say working hard join, and then taking break join. Now, because I'm doing a join, this is blocking the calling thread. So blocking calling thread. And I'm going to annotate this with @sneaky_throws because the join method throws an interrupted exception. Now, we need to set some system properties here because work hard and take a break will be scheduled as virtual threads. And because they are scheduled as virtual threads, they will run at the same time, but working hard will not really finish. I'm going to go to my run configurations. So I'm going to modify the run configuration. And here under -- enable preview, this is my JVM command argument. So -- enable preview. I'm also going to have -d, and I'm going to use those configurations there. So let me go back to the virtual thread implementation, and I'm going to use JDK virtual thread scheduler parallelism. So as I modify the run configuration, let me also add -d JDK virtual thread scheduler parallelism equals 1. So I'm going to set the parallelism 1. -d virtual thread scheduler, I'm going to say max pool size is equal to 1, and another -d JDK virtual thread scheduler dot min runnable is 1. Now this is also 1 by default. I'm going to simply call apply and then OK. Now, working hard routine, I'm actually going to call that from main. And because we only have one platform thread, obviously when I start work hard, this will start the virtual thread on top of the only carrier thread. Now, if this virtual thread worked nicely, it would yield some computational power to the other virtual thread to execute, and these two would work nicely and cooperatively. Now, because work hard is a CPU-bound task, which has a while true here, this will never yield. So let me actually run this and give you an example of how it would run. So let me run my application. So notice that we have working hard, and nothing else gets executed. So the taking a break doesn't actually get a chance to execute, and my computer is about to take off, which is why I'm going to stop this application from burning my CPU. So with one single platform thread and with a CPU-bound task, the virtual thread will never yield. So let me add a little comment here. However, there are instructions that we can execute in a virtual thread that will make it yield. For example, a sleep will force the virtual thread to yield control over the carrier thread. Let me give another example. So instead of working hard, I'm working hard, but with a bunch of sleeps in between. So I'm going to say a static thread work consciously, consciously. My spelling ability is a little bit stretched here. So while always true, I'm going to run this little sleep, duration of millis 100L. This will yield control. Now, I'm going to run a similar routine, such as working consciously and taking a break, and we'll see that the taking a break virtual thread will also have a chance to execute at the first yielding point of the first thread. So I'm going to say work consciously routine. I'm going to say work consciously and taking a break, and I'm going to call this one, so work consciously routine in main. And now we'll see that the taking a break function will have a chance to execute on the one thread that will run both virtual threads. So notice that we have I'm working hard, and at the first yielding point, the break will actually have a chance to execute. I'm going to take a break, done with the break, and then the work consciously will have a chance to continue its endless run. So yielding points are done with sleeps, for instance. Now, if your question is when can you control yielding points, there is a function called thread.yield. This is just a hint to the scheduler that this thread is willing to yield control of the processor. If we go thread yield inside the always true, so this will give a chance to other threads to execute. And if we run the working hard routine again, we'll see that the taking a break function will also have a chance to execute just as well. All right, so we have I'm working hard, I'm going to take a break, done with the break, and then the working hard routine is then free to continue its endless run. So the thread.yield is another hint to the thread scheduler to let the carrier thread take on some other virtual thread. So you can control yielding with thread.yield. However, yielding is not always possible. For example, if you work in a synchronized block and you run a yielding function or a blocking or semantically blocking function like sleep. Let me show you an example of that. So this is called pinning. And pinning a thread happens if you execute a code inside a synchronized block or method, or when you call a native method or a foreign function, for example, when you use Java native interface of JNI. Let me see an example of a pinned virtual thread. Let me simulate an employee at work that needs to go to the bathroom, and the bathroom only has just one spot, so the access to the toilet is synchronized. So we have one toilet in the office, and I'm going to have a static class, I'm going to have bathroom, and I'm going to have a synchronized function, so synchronized void use, and I'm going to say log using this bathroom, and I'm going to say sleep with duration of seconds 1L, and I'm going to say log done using the bathroom. So just a synchronized function to use this bathroom. Okay, now let me define a static instance of that. So static bathroom as new bathroom. Okay, now I'm going to have a static thread. Let's say go to the toilet. So go to bathroom. And I'm going to have return virtual thread with, let's say, going to bathroom. And the runnable is going to be a lambda, say bathroom.use. That's it. Okay, so just a virtual thread to go to the bathroom. Now, let me create two people that want to use the same bathroom at the same time. So I'm going to say static void, let's say two people racing to the bathroom. And I'm going to have a var Ricardo, who originally wrote this article. I'm going to say go to bathroom, and then I'm going to say var Daniel as go to bathroom again. And I'm going to say Ricardo join and Daniel join. So Daniel join. Now, usually when we call a sleep, normally this yields. But because we're inside a synchronized method, this will not yield. So the synchronized method will execute fully before exiting and then doing a yield. So I'm going to run the sneaky throws again so that we hide the exceptions here from joins. And I'm going to call this little method. Let's see how it actually works. Let's wait for the compiler, and notice that we have using this bathroom, done using the bathroom, using this bathroom, done using the bathroom. And notice that no two logs interleave. So sleeping does not actually yield, but all synchronized code will pin the virtual thread. So this code will pin the virtual thread to the carrier thread until it's out. So there you have it, folks, a comprehensive introduction to Java virtual threads since JDK 19. I hope you enjoyed this video. Check out the blog post for more information on the new log API, thread locals, new best practices, and some internals of how virtual threads actually operate on top of the JVM. If you enjoyed this video, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. And check out the Rock the JVM website. I have literally hundreds of hours of everything, mostly in the Scala ecosystem, but also in the JVM world in general. Until next time, folks, I'm Daniel, signing off.